So as I mentioned in your book, trying to remember, but I believe sort of all that stuff that, again, significant figures, conversions, density, um, how to properly take measurements and all that kind of stuff. Again, I believe in sort of like a pre-chapter in your book. We don't officially sort of cover it. So we're going to kind of officially cover it now. Like I said, just again, to make sure everybody hopefully is on the same page in terms of all those topics. Um, so technically speaking, what we're going to be talking about today, obviously, you are responsible for as well for exam two. You know, some of this stuff may be on there. So my hope is obviously it is maybe somewhat review for most of you, and it shouldn't be too difficult, I hope. But again, just to make sure everybody's sort of starting at the same point, we're just going to try to cover some of the highlights here of those topics. So I guess the first thing we'll talk about is just measurements. And again, I'm just going to kind of freehand the lecture here. So there really is no notes that goes with this other than what I'm sort of writing on the screen and stuff like that. But we'll talk about measurements. And obviously, when we do take measurements, a couple important things, right? Obviously, a measurement should have a number and units, and that's really important whenever you're doing chemistry. Is this is the part that seems to get lost a lot of the times, and you should always have units, you know, that go along with your numbers, um, because really, you know, if you just say, hey, I have 100 of something, you know, really, you know, what does that mean? You know, you had $100, that's very different than you had 100 pencils, very different than you had 100 pennies. So the units are really important, especially in chemistry and when you take measurements, to always be included. And they should always be included also in your calculations as well, um, because that is properly shown in all your work. And it also hopefully helps you um, figure out if you're doing the calculation right, if you actually have the units. If you just have numbers there, then you really don't, not really sure, you know, maybe where a certain unit is, what units are canceling and stuff like that. So you always want to keep in mind, especially obviously as you do anything in this class or really any science class or chemistry class, that you should always make sure you don't lose those units along the way. Um, because they're a very important part, not only just the answer should have units, but also the calculation part. All right, so let's then talk about actual measurements. So when we do take a measurement, especially when we're using um, some type of piece of equipment, there's always some degree of uncertainty. So no matter who you are, no matter sort of what sort of equipment you're using, depending on the equipment as to what degree of uncertainty there is, but there's always some degree of uncertainty associated with sort of taking a measurement. So for example, if we had like a ruler, my bad drawing of a ruler here. And we'll call this like one, we'll call this 2 like centimeters, for example. And let's just say we were kind of measuring this arrow. Now, when we would look at something like this, you always want to look at sort of the equipment that you're using, and you want to really figure out what does all the markings really mean. You know, what are the little markings mean? What do the big markings mean? So, for example, here, if we were to look at this, we would start counting really from here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it really is 10 markings between 1 and 2. And that means that each of the little markings here mean basically 0.1 centimeters, as this first marking would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2 as we go there. So when we look at a piece of equipment that we're using to make a measurement and we're looking to obviously make the measurement, there definitely should be numbers that, no matter who takes a peek at it, who looks at it, everybody should agree upon. And I would safely assume that if everybody looked at my little arrow here, everybody would agree that it's at least 1.1, it's at least 1.2, it's at least 1.3, it's at least 1.4. Maybe it's not so much 1.5, but it's at least 1.4. So when we would take this measurement, we would want to record 1.4. These are what are sometimes referred to as all the certain numbers. And what that really means is, again, no matter who sort of takes a look at it, everybody really should agree that, it is at least in this case 1.4. But now if we look at it, we could clearly see that it is not 1.4 on the nose. And if you look at it, maybe you feel like, hey, it's not really 1.5. This would be obviously 1.4. This would be 1.5. And this is where that sort of uncertainty comes into effect. I may look at it and go, I think it's kind of like halfway there between the two numbers, and I may record it as like a 5. Somebody else may say you're kind of crazy. Clearly, the point of your arrow is pretty close to the 1.5. That's more like an 8 or a 7, maybe. Some others may say, no, I think it's less than that. Maybe it's 4 or something like that. So there is a certain amount of uncertainty associated with this number. And this is what is sometimes referred to as the first uncertain number. And whenever you take a measurement, you should always record all the certain numbers and that first uncertain number and the units. And this, when you do that, is really what significant figures are. So I would call this 1.45 centimeters. Again, somebody may call it 1.47 centimeters because they feel it's closer, or 1.48, or even maybe 1.49, depending on how close you look. And the degree of uncertainty there is in the last digit. And because there is 3 digits there, that would mean that this number has 3 significant figures in this particular case. So you definitely want to always record all the certain numbers plus that first uncertain number. And that really is what makes up significant figures. And that's the proper way to take a measurement. Now, you got to remember that it does change depending on sort of the piece of equipment that you're using. So, for example, if we had I'm just going to go this way ish. We'll call this 10. We'll call that maybe 20. We'll do these as milliliters here. And let's just say we had a liquid in there. And imagine the rest of the other side of the container as well. So when we would look at this, what we again want to look at the scale, and we really would want to count up, how many lines we have between the two big numbers. Obviously, the big number here, 10 and 20. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, here we have 10 markings between 10 and 20. Difference here is 10, which means in each of these cases, each of these markings is 1 milliliter, the small markings. That would be 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So even though we still have the 10 markings between the two numbers, because the scaling is different on this piece of equipment, we actually do have a different value for what each of these little guys represent. Again, we could kind of approach it the same way. We could look at this, and by the way, this is a liquid in a glass container, which means you'll see this curvature of the liquid, probably better than I drew. And we always want to read it from what is referred to as the bottom of the meniscus, right? That's what is known as the meniscus. And it's that curvature exaggerated there. We always read from the bottom of the meniscus. And very butcherly spelled there. But what we want to figure out is what does each of those markings represent? Obviously, they each represent 1 milliliter, which means that's 11, that's 12, that's 13, that's 14, that's 15, that's 16, 17, 18, 19, and then obviously 20 there. So again, no matter who takes a peek at this, everybody should agree it's at least 16. Again, these would represent our certain numbers. Again, we get to a situation where, you know, it's not exactly 16. It's definitely not exactly 17 in this case. We have to make some type of estimate. So maybe I don't feel it's exactly halfway there. Maybe I feel it's almost halfway there and record it as like 16.4. Again, we would put our units here. This would be our uncertain number. And usually that uncertain number is like plus or minus 1. So what this is really saying is, you know, I think it's like 16.4. But, you know, maybe it's like 16.5 or maybe it's 16.3. It's somewhere in that ballpark. And if you look at the picture, that probably makes sense. You know, it's somewhere in that ballpark of 16.4, 16.5, 16.3. It's pretty much, you know, where that guy is. Again, because this is all the certain numbers and that plus uncertain number, we would know that this guy also has 3 significant figures. It's really important to always look at your scale because let's just say, for example, we had something like this. Let's do this. Make my nice drawing here. This is 10 milliliters. We'll call that 20 milliliters. And again, we'll put a liquid somewhere like this in there. And we'll go from the bottom of the meniscus. That's a really badly drawn. Let me fix that there. There we go. Probably because I curved it here, but we'll just kind of do this, I think. There you go. Okay, so we'll say we have a liquid in here, but now if we look at sort of the scale, that's 1 marking here, 2 markings here, 3 markings, 4 markings, and only 5 markings in this case. That's 5 markings, but our overall difference is still 10, which means in this case, each marking is actually 2 milliliters. This would be 12, this would be 14, this would be 16, that would be 18, and that would be 20. So even though we have the same sort of larger markings, we have a different number of smaller markings, which means that our difference here is going to be very much different than the scale above. Now, when we look at the bottom of the meniscus here, we could clearly, oh, geez. I'll try that again. There you go. I'm going to try to get that pen to work there. Let's go across. There you go. So if we look at the bottom of the meniscus, I guess, look somewhere right there. And we can clearly see it's 16. We could clearly see it's maybe not 18. So in this case, somewhere between 16 and 18, the best you could do is call it 17 milliliters. So what does that mean? Well, there's not enough room in here for you to know where like 16.5 is, 16.6, and then 17.1 starts, 17.2, 17.3. There's just too many markings for you to visualize and try to make a best estimate as to, you know, where it will stop and where it will not. The best you could do is go is like, well, it's kind of 17-ish. It's kind of between 16 and 18. So what does that mean when we record 17? There's 2 numbers here, which means this has 2 significant figures. That means that the 1 in this case is the certain number, and the 7 is the uncertain number. And that makes sense because if we think about sort of that plus or minus 1 and the uncertain number, we're saying, well, this could be as high as 18, which is clearly not, or it may be as low as 16, which it may be as well, but it's somewhere in that ballpark is the best we could do. There's no way we could go as like 16.5 because how do you know where 16.5 is? Is it here? Is it here? Is it here? There's no way to visually sort of represent that. So it's really important to sort of look at your scaling on things when you take measurements. And what you typically do, outside of say this example, but what you could typically do is go one more place to the right of the smallest marking. So what does that mean? Well, in this case, the smallest marking was 1 milliliter or one. We were able to take the reading one more place to the right to the 0.4 or 0.1 sort of spot. In the previous example, the smallest marking was 0.1. We were able to take the reading to one more place to the right of the smallest marking. So we're able to typically, in most cases, take our reading to one more place to the right of the smallest marking. Any questions on that there? So what happens if you, and I'll just steal this guy here since we got it. What happens if we take our same sort of ruler here, but we were measuring something like this here? Like you feel it's dead on right there, that 1.4 marking. Well, we would have our same sort of theory here. Our smallest markings are 0.1. And what would you record? Would you record 1.4 centimeters? Would you record 1.40 centimeters? Would you record 1.400 centimeters? So in this particular case, this is wrong. There's too many. It's one of these two things is where we should record it. Well, when we look at it, because we have the ability, or because the smallest marking is to the 0.1, as we've been talking about, we pretty much can take the reading to one more place to the right, which means in reality, we should record 1.40 centimeters because we have the ability to do that on that particular scale. Now, you may be asking yourself, is there really a big difference if I write 1.4 or if I write 1.40? And the answer is there actually is a big difference in terms of what you're telling somebody when you would write 1.4 versus 1.40. And I'm going to try to explain that to you right now. So let's take a look first off at if you decided, hey, I want to record this as 1.4 centimeters. What that would tell people is in this measurement, there is only two significant figures, which means that the certain number would be the 1. The uncertain number would actually be the 4. You may be saying still, is it a big difference? Well, what we've been talking about is in general, we consider the uncertain number to be sort of plus or minus 1. And what you would telling people if you recorded the number as 1.4 is, well, it is 1.4 centimeters, but it could be as big as 1.5 centimeters, or maybe it's as small as 1.3 centimeters. Now, if we look at our actual guy right there, right, we could clearly see that it is really nowhere near 1.5 centimeters, and it's really nowhere near 1.3 centimeters. So by saying 1.4 without the extra 0, we're basically making this measurement a crappy measurement. We are like, there's a lot of, it could be anywhere in this range, which clearly by looking where it's at, it's not anywhere in that big range. But we're telling people, could be a pretty big range of where you can find that actual measurement. How does that change when we actually do the correct measurement and put in our number as what it should be in this case, 1.40 centimeters? Well, 1.40 centimeters means that this number has 3 significant figures. Also means that the 1 and the 4 are our certain numbers, and the 0 is our uncertain number. And what that means is when we think about a number like 1.40 centimeters, we're saying that this number could be as big as 1.41 centimeters, or as small maybe as 1.39 centimeters. Now, when we look at our picture, that makes a lot more sense and is a lot more accurate in terms of what we're looking at. 1.39 is like right here, right? Like right there ish. 1.41 is like right there. And that pretty much is on the actual measurement that we took. And by lopping off that 0 here, thinking it's not that important, we're telling people that, you know, that little guy could be anywhere in this region or this region, and it clearly is nowhere near there. So it's always really important. It's a very common mistake that people make when they do take measurements is, you know, they just go, well, it's dead on. Why do I need that 0? It's not that important. But it really is important in terms of how good or how bad your measurement is. Again, taking out that 0 actually makes your measurement pretty crappy, and you shouldn't do that. So if you find yourself and you're taking a measurement and you feel like it's dead on a number and you have the ability to take it to one more place to the right, you should do that, and you should include the 0 because it's important for significant figures. It's important for how sort of accurate and good your measurement or precise your measurement sort of is. Any questions on sort of taking measurements properly and stuff like that? Now, speaking of sort of accuracy and sort of precision, you know, sometimes those words are sometimes confused when people think about measurements and sort of what those sort of words mean. When we talk about accuracy versus precision, there is a difference between those sort of two words there. And the difference is if you're accurate, basically what that means is how close you are to the true value. So if you say that was a very accurate sort of measurement, that means you measured it pretty close to what the true value should be. Precision is how close a set of numbers are to one another. So to illustrate this is the common example like bullseye, right? You throw darts at a board, right? The goal is to hit the bullseye. If you throw your darts and you end up with a dart there, maybe a dart there, maybe a dart off the board, you're not very accurate, as you obviously didn't hit the true value, which is what we're going for, the bullseye. You're not very precise because it's clearly all over the place. So then you go, all right, I'm sorry, we'll do double or nothing. You know, it's my first one here. Let me try it again. So you pick up your darts and you throw them again at the dartboard, and you go boom, boom, boom. You are not very accurate because accuracy would mean hitting here in the bullseye. But you are very precise. You precisely miss the spot every single time in the same location. So this illustrates that you can be very precise and wrong, right? You could like do an experiment the wrong way multiple times, right? When you do experiments, sometimes you do multiple trials, right? And that's really looking at precision. You know, when you do multiple trials, you're looking at how precise your measurements are. Are they repeatable and stuff like that? So in this particular example here, it is very repeatable. Unfortunately, it's just not very accurate. You basically did it wrong every time the same way. And you can definitely, as you can see here, be very precise and not very accurate in that sort of case. So you go, all right, triple or nothing here. take up your darts and you throw them. And actually, we'll change the color of my darts so I can see them. I think we'll go with maybe green. We can see. I don't know. Boom, boom, and boom. In this case, we are very precise, as obviously we all hit pretty close to each other. So this is sort of repeatable, and we're very accurate in this case because we hit the bullseye here. So a lot of times if you're accurate, you probably have a fairly good degree of precision that's occurring with your measurement. But again, we do look at sort of precision when we do multiple trials. Sometimes we calculate things like percent precision. It gives us an understanding of how repeatable an experiment is. Sometimes we calculate for accuracy what is sometimes referred to as percent error. Percent error is basically how close you are to the true value. And when we calculate something like percent error, we typically are looking for a small number as a helpful number in terms of that. Any questions on the difference between accuracy and precision? Okay. So going back to our significant figures conversation there a second ago, again, when we properly take a measurement, and by the way, when we do take measurements, as was referred to as a quantitative observation, quantitative meaning numbers and stuff like that, qualitative meaning observations, no real numbers. But when we figure out a proper measurement, how many significant figures there are rules for counting significant figures. So first off, the first rule is pretty simple. Anything that is a non-zero will be significant. So any number that you have that you start counting, we count left to right. As soon as you hit that very first non-zero, so we would start counting here. That obviously is a non-zero. Would count as to being significant, and all four of these guys would be significant. So this would have four significant figures here. Now it's the zeros that sometimes really confuse people. And there's three different types of zeros. There's the first one, which is sometimes referred to as a leading zero. I guess we'll call it a leading zero. And those are all the zeros that come before you hit the first non-zero number. So again, going left to right, all the zeros that happen before you start hitting that non-zero number, these guys are not significant. So for example, if you had 0.000159, we would count going left to right, and none of these zeros would be significant. We want to start counting until we hit this very first non-zero number, which is 1. And there's 1, 5, and 9, which means that all three of these part of the number are significant. This guy would have 3 significant figs in this guy's. Now, the next type of zero are zeros that are essentially trapped between two non-zeros. These are sometimes referred to as captive zeros. And these are, again, numbers that are trapped between, or zeros that are trapped between two non-zero numbers, and these guys are significant. So an example would be if you had like 6.0006. Again, we would start counting here, and that is a non-zero, which means they're significant. All these zeros that are sandwiched between the two sixes there are going to be significant as well, finishing with this number here. That gives us 1, 2, 3, 4, 5 significant figures in this particular case. Lastly here, really the zero that gives everybody sort of the hardest time in terms of, is it significant, is it not significant? And that is the zeros that really do come at the end of a number, and those are sometimes referred to as trailing zeros. And these guys may or may not be significant. And what determines whether or not they're significant or not is they will be significant if there is a decimal place in the number. So if there is a decimal place in the number, it doesn't have to be near the zeros, but really anywhere in that number, all the zeros that come at the end will be significant. So if we look at like, for example, here, all right, so 600 written like this. This is one significant figure here. These are zeros at the end. There is no decimal point written in this number, which means this has one significant figure. And what that means is this number could be as big as 700 or as small as 500, as opposed to if you wrote the 600 with a decimal point there. This would be significant. Now these zeros that come at the end are significant because there's a decimal point there, and this would be 3 significant figures. Again, the difference here in terms of significant figures is, as I just mentioned, the top number means that we're got a range of like 700 to 500 in terms of where that actual number could be, as opposed to the last guy there, we got a range of like 601 to like 599, and that's again a much smaller range. So the more you could take a sort of higher significant figure sort of measurement or something like that, sort of the better the number is. Any questions on that there? So these are significant figures, which goes with really measurements. There are some numbers that we really don't measure per se. So these are obviously usually for measured sort of numbers. So for example, if I had, like 4 square cubes on my desk or something like that, or 3 square cubes on my desk. And if I had these guys sitting on my desk, there's really not going to be any type of experiment measurement that I'm going to do to figure out how many I have. I'm going to simply count them, right? So anything that's counted are definitions also apply in this area. Like there's 12 inches in 1 foot. That's a definition, right? That's an equality. These guys are what are referred to as being exact numbers. And exact numbers have pretty much unlimited sig figs. You basically can sort of count them as much as you like in terms of significant figures as to however many you want. The nice thing about exact numbers is, especially we come across them with definitions, when we're doing calculations involving significant figures, we don't really worry about the exact numbers. So anything that's considered an exact number, you don't have to worry about it in terms of the calculation and in terms of what your answer should be when you do those calculations. Now, when we do calculations with significant figures, which is oftentimes sort of how we deal with them, a reminder of sort of the rules with sig figs and calculations. There's really kind of 2 groups of things that we do. We either multiply and divide, or we add and subtract or subtract. So these are really the 2 sort of groups of stuff that we do. And when we're dealing with how many significant figures our answers should have, when we multiply or divide, the answer should have the same number of significant figures as the number with the least number of sig figs. So again, that means that if you took a number like 32.0 and you multiplied it by 1.256, in this case, this has, again, 3 significant figures. The 0 is significant here because of the decimal point. This guy has 4 significant figures. All of them are significant. That means the answer should end up with 3 significant figures. So if you multiply or divide the least number of significant figures in any of your measurements is how many significant figures your answer should have. The reason for that in both of these cases is because basically your least one is your worst measurement. So your grand total of all your measurements that you do is only as good as your sort of worst measurement. And that's why we look at the least number of sig figs here. When we add and subtract, we're actually looking at something slightly different. We are looking at actual decimal places. So when we add and subtract, the answer should have the same number of decimal places as the number with the least number of decimal places. So when we add or subtract, again, we're not looking at sig figs, but we're actually looking at decimal places. And the smallest number of decimal places is what our answers should end up with. So if we took 1.25 and added it to 2.0 and added it to 3.256, when we would do this addition here, we would end up with 6, I think, 0 and 5.35 and 6. I didn't use my calculator, so hopefully that's right. Here you may be tempted again to go with sig figs, but we're adding, so we're going at only decimal places. This first number has 2 decimal places. This number has 1 decimal place. This number has 3 decimal places, which means the smallest number of decimal places is right here at that 5. And that means that the correct answer here should be 6.5, whatever that unit is associated with there. So multiplying, dividing, you're looking at significant figures and it is the smallest. Adding and subtracting, you're looking at decimal places and it's the smallest. It's important to remember on the right-hand side there, we go to 1 decimal place because the 2.0, but that gives us an answer of 6.5, which is actually 2 significant figures. So, keep that in mind as to what you're asked. Also, sometimes and very common in obviously chemistry and stuff like that is we really do multiple steps sometimes in a calculation at once. So if you had sort of a multiple step process, the key rule is you kind of just want to keep track of everything. So for example, if I were taking, 33.6 times 1, 2, 3, 4, divided by 5, 6, 7, 8, 9. I am counting in case you're following along. The typical thing that we would do here is what's in the parentheses first. So in the parentheses, we're multiplying, which means we should be looking at significant figures. That is 3 significant figures on the left. That is 4 significant figures on the right, which means technically speaking, when we do get an answer for the top part, we should end up with 3 significant figures. Then technically speaking, we're taking 3 significant figures on top and dividing it by 5 significant figures on the bottom. Again, here, since we are dividing, we're looking for sig figs and the smallest number of sig figs, which means our answer should end up with 3 significant figures when it's all said and done, whatever that number may be. So if you're doing multiple calculations, multiple steps, what you want to do is keep track really of sort of your significant figures, and you want to clean it up when it's all said and done at the end. You do want to avoid rounding along the way, or really um, extreme rounding along the way, because if you're doing multiple step sort of calculation, every time that you do a little bit of rounding and get an answer, and then you take that answer and do another calculation, you round that answer, take that answer, do another calculation, do some rounding. Every time you sort of round yourself, you're probably moving your answer further away from the correct answer. So it's a good general rule of thumb, especially when you're doing calculations, to not do a lot of rounding until the very end. And that's why we say, it's really good to keep track of your kind of significant figures and stuff like that throughout the calculation. And then you could, again, sort of clean it up at the end to the proper number of significant figures. Question on significant figures and sort of calculations involving significant figures. Now, we talked a little bit about this next little idea here before, but again, just to make sure everybody's on the same page and how to properly write scientific notation. I'm surprised by how many times I see people not knowing how to properly write scientific notation. Scientific notation is a way in science, and especially chemistry and such, that we basically use for really large numbers and really small numbers. Because really large numbers, really small numbers typically will have a lot of zeros. So if you try to do sort of calculations involving those numbers, you'll end up perhaps with losing a zero along the way, adding a zero along the way, or something like that. So we use scientific notation to help us do that. And scientific notation is in the general form of n times 10 to the n. The importance of this is that the first n here, the big N, is a number between 1 and 10. And that's the proper way to write scientific notation. You shouldn't write like 400 times 10 to the 3 or something like that, or, point something times 10 to the 4. It really should be a number between 1 and 10. The N up here is a whole number that can be positive or negative, again, depending on sort of which way that you are moving the decimal point. So if I had a number like 42256, although there's no decimal point written here, in the terms of scientific notation, we would assume it's here. And we would need to go one place to the left, two places to the left, three places to the left. If I stop there at 42 point something, 42 point something is not a number between 1 and 10. So I need to go one more place. That gives me 4 point something. And I do get a number between 1 and 10. And that would be 4.2256 times 10. And I moved it 1, 2, 3, 4 places to the left, and that would give me 4.2256 times 10 to the 4. It is a positive exponent when you move it to the left, or another way you can remember it is big number positive exponent. And that would be different if I had 0.0001250. And if I did this, we would need to take the decimal point one place, two places, 3 places, 4 places, and 5 places. And that would give me a number of 1.250 times 10 to the minus, and I forgot how far I went there, 1, 2, 3, 4, 5, minus 5. Here, negative 5 meaning it's a small number, moved it to the right, and we end up with that. Now, you may also be wondering, why maybe I kept all those numbers, why I did not keep maybe some of the numbers when I converted into scientific notation. And the reason is when you write a number that's in scientific notation, the entire number that comes before the times 10 part, so this part of the number here, that number is always significant. So what does that mean? Well, when we take a number that's written in positional notation, sometimes called, or decimal form, regular form, and take it to scientific notation, we should never lose significant figures when we do that. So if I were to look at this first number, that is one significant figure, two significant figures, three significant figures, four significant figures, five significant figures. That means when I come over here to my number written in scientific notation, that is one significant figure, two significant figures, three significant figures, four significant figures, and five significant figures. Again, same number of significant figures on both sides. We don't lose anything along the way. Same thing if we look at the bottom one. All these zeros are leading zeros, which means they're not significant. This is where we would start counting, and that would be one significant figure, two significant figures, three significant figures. This zero that's at the end is significant because there's a decimal point in this number, and that would be four significant figures. When we go to our scientific notation, one significant figure, two, three, and four significant figures. So it's really important that as you go kind of from scientific notation to decimal form or decimal form to scientific notation, that you don't lose any significant figures along the way. And it's really for the same reason as before. If I were to just go 4.22 and rounded the rest off, I am again making really that number worse or measurement worse by taking out a number of significant figures. Any questions how to properly write scientific notation? Now, more importantly, I think for this class and probably most classes that you take is how to punch that into your calculator. And I think we've gone over that, but one more time, just to make sure. When you type a number that's in scientific notation into your calculator, you should be using your exponent button, and that is your EE button, that is your EXP button. And again, if you have a newer sort of calculator, you may even have one that looks something like that. Now, when you use these buttons, it's important to do it sort of correctly. So if I had a number like 4.25 times 10 to the minus 4, and I wanted to enter that into my calculator, if I had one of these two buttons, I would enter 4.25. I would then hit that exponent button. And most likely on that calculator, it will pop something like this up. And then I would go, when you do that and you see the E or you hit this button, that represents this part of the number. So when you hit either one of those buttons, that represents the times 10 part of the number, which means you should not hit the multiplication button. You should not hit like the second log button, shift log, or anything like that. You then should use your negative button in this particular example, which looks something like this, not your subtract button. And when you do that, we'll then go negative, and then you can put 4 there and fill it out in that particular case. Now, if you use those buttons, you should be in good shape. You want to make sure that you do that. Again, if you see your answer is sort of correct on the first part of the number, but like the exponent part, when you do some calculations are not correct, then it's probably the way that you're kind of putting it into your calculator. If you have a newer sort of calculator, one that does have this type of button, you basically kind of do the same thing, except that because of the way those calculators are typically programmed, you do need to make sure that you put parentheses around every single number that you're going to put in scientific notation. So if we're going to put the same number, I would start with opening a parentheses. I would type 4.25. You'll hit that number, and I believe on your calculator, you'll get like a 10, and then you'll have the little guy kind of blinking up there once you hit that button. When you have that guy blinking up at that button, you then could do the negative and 4, and it will turn this into 4.25 times 10 to the negative 4. your little, and we would have the parentheses, your little cursor would be here probably blinking. And in my experience, you then need to actually bring the cursor kind of down. And to do that, you have a button on there that's like a little circle, kind of almost looks like this, I think. And usually, if you kind of hit the right hand side of that circle, it will bring this cursor down, and then you'll be left with 4.25 times 10 to the minus 4, and it'll be blinking down here. You could close the parentheses at that point, and then you would have your number properly put in there in scientific notation. So if you have one of those newer sort of calculators, you do have to kind of put parentheses usually around everything for you to get everything sort of correct. We're gonna talk about rounding here in just a second, so I'll get to your question about rounding and sort of the proper rate of rounding in 1 second here. Um, so you want to make sure you definitely use those exponent buttons, especially really important in this class. Otherwise, you will definitely be off. And I saw some of that, I think, as I was grading some things. You want to make sure that you definitely punch these things in correctly. So just to make sure, why don't we do one here together, a couple here, just to make sure everybody gets the right sort of numbers and punches them in correctly. Um, why don't we do, let's do 3.25 times 10. Let's do minus 7. And we'll divide it by 5.2 times 10 to the, we'll do 20. And then let's do 1.25 times 10 to the 7 times 6.5 times 10 to the minus 22. All right, I'll do them as well. You do them as well. Again, make sure you use your exponent button. Okay, so let's take a look and see how you did with your calculator here. Something to write with. So again, on my calculator, since I have the EE button, and again, this works for EE button or EXP button. And again, if you have that other button, kind of the same approach. You just got to make sure you put the parentheses around everybody's numbers. So if I were to do this, I get my pen to write here, I would punch in 3.25. I would then hit the exponent button. Again, that takes care of this part of the number. So there's no need to put the multiplication button or anything like that. I would then hit my negative button, which looks like that, or again, it may look like this. And then 7. And on my calculator, it would show it as 3.25 E minus 7. Again, it may show it as 3.25 minus 7 up on top, something like that. I obviously would then hit the divide button and punch the next number in the same way, 5.2. Again, my exponent button, and in this case, it's a positive exponent. So when I hit that exponent button, again, taking care of that part of the number, and then I would just hit 20 and then obviously hit the equal sign. And if I do all that good stuff there, looks like I end up with a number on my calculator of 6.25. And you don't want to forget the exponent part, times 10 to the minus 28. On my calculator, it displays it like this. When you go to actually write it as an answer, you really shouldn't write it with the E. You should then turn that E back into times 10 part. So again, even though your calculator may give it to you, and that's what E sort of represents, you really should turn it back into the times 10 part when you're given the answer or sort of writing the answer in scientific notation. Now, first off, any questions on that calculation or that number there? The other thing that we want to also look at is significant figures, right? So when we are going to give our answer, we are dividing here, which means we're looking at significant figures. The first number has 3 significant figures. So remember, in scientific notation, all the numbers that come before the times 10 part are significant. The second number is 2 significant figures. Again, the numbers before the times 10 part, which means really our answer should only come to 2 significant figures in this particular case. So we do need to do some rounding, and really we should give this answer as 6.3, as this is a 5, which means we should round this guy up by 1, times 10 to the minus 28. Any questions on that there? Again, putting the bottom guy in the same way, we would do 1.25. I would hit my exponent button. I would hit 7. I would then hit the multiplication button, and then 6.5 exponent button, negative button, and 22 and equals button. And if I do all that good stuff on that guy, 1.25 E7 times 6.5 E minus 22. On my calculator, again, I get 8.125 E to the minus 15. Again, we should not leave that E. That should then be transformed into 1.25 times 10 to the minus 15. And again, we do need to look at significant figures. So looking at this one, we are multiplying, which is why we're looking at Sig Figs. 3 significant figures there, 2 significant figures there, means really my answer should be 2 significant figures here. And that means that really the correct answer should be 8.1 times 10 to the minus 15. Question on scientific notation. Again, important to make sure you know how to properly enter these into your calculators. If you're still struggling with that, sometime during one of these lab periods coming up, make sure you reach out to me and we'll try to find it on your calculator. But it's really, really important to make sure you punch these things in correctly. Otherwise, what you typically will find if you're not punching these things correctly, as I mentioned before, is you'll look at this part of the number and go, oh, that's pretty good. But this part of the number will be off. And that's usually a pretty good sign, like I said before, that it's probably the way that you're punching that into your calculator as to why you're kind of off. Any questions on scientific notation? Now, do you always have to give the answer in scientific notation? And the answer is no, you don't have to always give it in scientific notation. You do have to give the answer to the correct number of significant figures. And if you could do that in sort of decimal form, that's perfectly fine. If you want to do it in scientific notation, that's perfectly fine as well. You don't have to give every answer in scientific notation. There may be situations, though, where the only way to get it to the proper number of significant figures is to write it in scientific notation. So there are certain situations where you can only kind of get it to the right number by doing scientific notation. So keep that in mind as well. And clearly, if the instructions say give the answer in scientific notation, then you should. But you don't have to if there's no type of instructions involving that. Any questions on that there? Okay, then let's talk a little bit about rounding, which I think was a question that came through there, and hopefully this will answer your question as well. So we do our normal sort of rounding rules, right? So rounding, less than 5, we sort of drop all the numbers, right? And if it's above 5, we round up. So that's pretty basic in terms of the rounding aspect of it. We do want to avoid a couple of things. If we say we have something like, excuse me, 13,333, and I want to round this guy just randomly to 2 significant figures. So take a moment and think about what the answer here should be if you round it to 2 significant figures. So I'll give you a second. I take a drink here. Okay, so if you rounded this to two significant figures, it would take you to here, and some popular answers, maybe 13. Other answers, maybe 13,000, maybe 13,000, uh, maybe 1.3 times 10 to the fourth. So, which ones of these numbers would be appropriate to go to two significant figures? So let's take a look and sort of analyze what is happening here. Let's take a look at the first one. So the first one definitely has two significant figures, right? So the 1 and the 3 are two significant figures. So that's good, right? Check. Two Sig Figs. Now, before we get off celebrating, we're not very happy probably with this number because of a couple of things. Let's just use a very common example. I don't know if it's a common example. Let's use a sort of logical example here. Let's say I owed you $13,333. And I say, no problem. I'm going to pay you two significant figures and I give you $13. I'm probably not going to get out of the room, I imagine, with that. You're probably not going to accept $13 for $13,333. There is a tremendous difference in the meaning of those two numbers. Although you did get it to the right number of significant figures, there is a big difference between $13,333 and like here's $13. We're all square. Everything's good. So you want to really avoid, I call this kind of extreme rounding. Sometimes this happens a lot. People try to get to the right number of significant figures and just go, I got to get the Sig Figs. I got to get the Sig Figs. And they end up basically changing the meaning of the number. So you should never change the meaning of the number because those two things, again, do not represent the same thing. Now let's take a look at this guy, 13,000 with a little decimal point there hidden at the end. That means that this is significant, and because there's a decimal point in this number, that means the rest of these zeros are also going to be significant. And that means that in this particular case, this has now 5 significant figures, which is obviously not good since we are shooting for two significant figures in this case. So even though it has the right meaning here, this has 13,000, it is the right meaning-ish, and it has too many significant figures, so it would not work. Let's take a look at the next way I wrote 13,000, which is 13,000 with no decimal point. 13,000 with no decimal point means that these two guys here are significant. The zeros at the end are not significant because there is no decimal point written anywhere in this number. So this guy would have two Sig Figs. That's a check. And now if I owed you $13,333 and I gave you $13,000, you probably would be okay with it ish. Give me the $333 teacher discount, it basically means the same thing, right? So the meaning here is the same, which means this is an appropriate way to round that number to two significant figures without changing the meaning of that number. Now let's take a look at the last one there. Last one, remember, as we were just talking about, all the numbers that come before the times 10 part, when you write a number in scientific notation, are significant. So this basically has two significant figures. And it's still, if you expanded it out, it would expand out to 13,000, just like over here. 4 places to the right, taking that zeros back out. And it has the same meaning. So this is another appropriate way you could do that. So these two ways on the right are a way that you could round these numbers to the proper number of significant figures without changing the actual meaning of the number. And that's really important Again, you never want to change the median number in an effort to get the right number of significant figures. You should also, as we talked about just a second ago, you should avoid really rounding a lot, especially if you're doing multiple steps in a calculation, again, to the very end, because as I mentioned before, if you get a number, you do a lot of rounding, and then you get another number, do a lot of rounding, and keep using that rounded number, rounded number, rounded number. Again, you will find yourself probably in terms of your answer, maybe fairly off of what the correct answer may be. So it's really important to make sure that you sort of round at the end, but you should definitely keep track of everything else at the end. So to sort of answer your question, I hope that answered your question, but if not, let's just take a look at sort of that number there that you put up there. And if your question is, in this particular case, should we always round to 3 significant figures? The answer would be no, you shouldn't always round to 3 significant figures. It is based on the calculation. You may or may not need to round that. But if your question was if I wanted to round this guy to 3 significant figures, if we wanted to round this guy to 3 significant figures, which I think might be your question, 3 significant figures would take us to here, right? So that is 3 significant figures. And what that means is we then need to actually look at the number that comes after this. And we see that the number that comes after the 9 is actually a 6, which means we do need to round that 9 up. But that 9 would then round really to 10, which would then round this guy up to also 10, and then round this guy up to 40, basically. And the answer that we would want to give if we were shooting for 3 significant figures would be 40. Would it be 40.0? I think that's all your options probably. So the answer would be, in this case, if we're going to 3 sig figs, this is not 3 significant figures. That would be 1 sig fig. If we did 40 like that, that still would not work because that would then be 2 sig figs. We would need to do 40 like this. Again, significant figure 1. 0 that comes at the end is significant because there is a decimal point in the number. Second 0 that comes at the end is significant, again, because there's a decimal point in the number. And this would be sort of that answer rounded to 3 significant figures. Questions on that? And obviously, depending on sort of the math that you're doing, either multiplying or dividing, adding or subtracting, then obviously that will determine how many sort of sig figs your answer should have, and probably the appropriate rounding that you should do. Any questions on significant figures, calculations with significant figures, scientific notation? Okay, the next thing we're going to talk about then is another really important skill that you hopefully should have picked up along the way, and really how you should be showing your work really in this class and most chemistry classes that you do. And what we're talking about here is sort of what is referred to as dimensional analysis. And dimensional analysis is really a fancy word for kind of conversions and conversions sort of factors and stuff like that. So let's talk about let's talk about actually conversion factors and sort of where they come from. So the first thing that we have is what's sometimes referred to as an equality. An equality basically is 2 different sort of measurements on different scales, but represent the same thing. So obviously, a very simple thing is 100 pennies, right, equals $1. They are on different scales. One's a penny, one's a dollar, but they do represent the same amount of money, right? 100 pennies is $1, and $1 is basically made up of 100 pennies. You could go through the drive-through and pay all in pennies. They probably will put your picture up and not let you through again, but you could technically do that. It's money. And you can pay in dollars, which they probably would let you back through the drive-through and stuff like that. From any type of equality, we really can write two conversion factors, and conversion factors are really just fractions. So we could say there's 100 pennies up on top divided by $1 on the bottom, or $1 on the top is 100 pennies here on the bottom. And we use these conversion factors. You won't use them both, but we use these conversion factors in a system known as dimensional analysis, where we use them as units. Unit A, we'll call it. So say we have one unit, we'll call it unit A, that we want to get rid of. And we basically want to use it as a conversion factor where we go unit A is unit B, sort of a relationship between them. And what we're doing here, and sometimes people are confused about sort of mathematically what's happening here, we're basically multiplying these things. Even though they're not written as a fraction, the first guy, it is basically a fraction. So we're multiplying across the top and dividing by what's on the bottom. So when we divide by the bottom, unit A divided by unit A, it equals 1. It's like when you take 2 divided by 2, it equals 1. When you take unit A divided by unit A, it equals 1 as well. They cancel each other out, basically. And we would be left with unit B in this case. And that's what dimensional analysis is, showing all the units with the numbers in this sort of fraction form and everything canceling out. And that, for the most part, is how you should do a lot of your calculations, is showing the dimensional analysis part of it and the units and units canceling. So obviously, if I had $5 and I wanted to know, how many pennies that was, I would start with $5. And remember, to get rid of units, it's always opposite. So again, even though the dollars is not written as a fraction, the dollars are on top, which means in order for it to properly cancel, we would need to use the conversion factor where the dollars are in the opposite location and would be on the bottom. When we would do this, technically we would be taking 5 times 100 and dividing it by what's on the bottom, which is $1. In this case, the dollars will cancel, will give us 500 pennies. Now, a couple of things about this sort of simple example here. First off, like I said, this is basically a fraction, even though it's not written at dollars are on top, we do go opposites. We want to think about sig figs for our answer. And when we look at this, this is a definition, as we talked about before, which is basically an exact number, which means in most cases, we do not even worry about this in terms of significant figures, which means the only number that we have to worry about in terms of significant figures is this first number, which has one significant figure, which is why I wrote my answer here as 500 with no decimal point, one significant figure in this case. You obviously could write 5 times 10 to the 2 pennies as well. And that would also be one significant figure. So when we come across a conversion factor like that, it's almost a safe bet to consider it an exact number. You don't have to worry about it, which means in most cases, what we're really looking at is the original number. The original number is probably, I would say 9 times out of 10, or even maybe higher than that, probably the right number of significant figures you should have in your answer. I will make a little note that when we talk about sort of conversion factors or equalities, there's really 2 types of system of units that we deal with, right? And the 2 types of system of units is the English unit that we use and basically the metric system. And between the English and the metric system, obviously, as countries did a lot more business and stuff with each other, we ran into some issues here in terms of some people are doing it in metric, some people are doing it in sort of English, some sort of units of measurement, and it creates some issues. So like in 1960, they had a conference on weights and measures. Sounds like a fun time. And they actually came up with a system of units that you may have heard of, which is the SI system of units. The SI system of units is the International System of Units, basically is what it stands for. It is pretty much based off the metric system, pretty much. And we typically use these sort of SI units in terms of conversions and stuff like that. But what I'm getting to in terms of looking at these sort of definitions is, technically speaking, if you're using a definition or a quality that is a English to English conversion, like, I don't know, feet and inches or something like that, or you're using like a metric to metric conversion, like grams to kilograms or something like that, you pretty much can consider those exact numbers. You don't have to worry about it. Technically speaking, if you do a conversion between like an English unit and a metric unit, you technically should look at the number of significant figures in that sort of conversion factor. For most of my classes I teach, I don't worry about that. So I'm just telling you what really you should do is, if you're actually doing sort of an English metric sort of conversion factor or using one, you kind of should look at the really sig figs that are involved in that one. But for our class, you don't have to worry about that. In a lot of chemistry classes, you don't have to worry about it. But the correct way is, if you're kind of using a conversion factor that involves both of these sort of system of units, you really should look at the significant figures. Is not necessarily considered a exact conversion because of that. The only one that really is 1 inch is like 2.454 centimeters. That again is a English to metric sort of conversion, but that's considered an exact sort of conversion and is still considered an exact number. But technically all the other ones you should, but you don't have to worry about that for our class. Pretty much if you see any type of equality that you turned into a conversion factor, you can pretty much safely consider it an exact number, which basically gets us back to what I just mentioned earlier. Pretty much all of, if you're just straight doing conversions, pretty much that original number is probably where you should be looking at in terms of, how many significant figures your answer should have. Any questions on sort of dimensional analysis there? So it's really important as well. And I would say, let's talk about some common errors that sometimes people make when they're doing dimensional analysis problems. So let's just say we set it up, and I'm just going to use random numbers. It really doesn't matter. 425 to 6 and 725 to 8. And you got all these sort of conversion factors that you're using back to back. And, you want to kind of punch them all into your, I guess that would be 1. That's probably not a good choice. 325. Now, technically what you should be doing here is, again, you're multiplying across the top. So technically you should be taking 325 times 425 times 8 times 125. And then you should be dividing by what's on the bottom. 6 times 725 times 325. Now, what happens when people go to punch all these things into their calculator is they don't want to wait, I guess, or want to do it all at once. So they actually do. Sometimes people will punch it in just like this: 325 times 425 times 8 times 125 divided by 6 times 725 times 325. And they'll end up with the wrong answer. And that's because, technically speaking, you got to put parentheses in the right spots, right? You got to kind of parenthesize the bottom there. And then you probably will end up with the right answer. You can even parenthesize the top and you'll be okay. Now, the safer move to get yourself probably to the right answer is, to be honest with you, you could take the top numbers and multiply as many numbers as you want together. The key is, once you hit the very final number, you should hit the equal sign. And that will give you a number, obviously. Then the safest approach, especially when you have multiple things like this, and depending on your calculator, depending how you punch stumps in, is to actually hit the divide button and divide it by the first number, and then hit equals. Then hit the divide button and divide it by the next number, and then hit equals. Then hit the divide button and divide it by the last number, and then hit equals. If you sort of do it like this, you definitely will get the right number. I can't tell you how many times I've seen people really just try to, kind of punch it all in at once. And they're always surprised, like, whoa, I'm like nowhere near sort of the correct number. And it really is, based on how you punch it in. If you don't really use the parentheses correctly and punch it in correctly into your calculator does some weird math. It decides, oh, you want to multiply everything on the top, and then you want to divide by the first number, get an answer, and then multiply it by the next number, get an answer, then multiply by the next number. So you end up doing sort of the wrong math that way. So in my experience, if you have multiple things you want to sort of multiply and then divide by, you can multiply as many numbers as you want across the top. Doesn't really matter. You don't even need parentheses. You can hit all the numbers across the top. The key is to hit equals once you hit that last number, then divide by the first number on the bottom, hit equals, divide by the second number, hit equals, divide by the third number, hit equals, and you will pretty much 100% of the time end up with the right answer if you kind of do it that way. So again, what I'm trying to stress to you is sometimes people make errors because really they don't know how to properly punch things into the calculator. So you want to really be careful as to how you punch it in. And sometimes punching too much in at once does not end up really well in terms of your final answer. Question on sort of dimensional analysis and how to punch it in conversion factors. Again, a reminder, if you did have something like this, by the way, and obviously there would be like units associated here, right? We'll just call it B, call this C, call this D. Unit A would cancel, unit B would cancel, unit C would cancel. You would be left with whatever your answer is in units of D, whatever that may be. Now, you could do all this calculation in one step. You could do individual steps and do the first part, get an answer, take that number, do the second part, get an answer, take that number, do the last part, and get an answer, which obviously would have units of D. Again, if you sort of do it by piecework, as we were talking about, you do want to make sure that you don't round a lot at these steps. You want to keep in mind what sig figs you're looking for, but you pretty much don't want to round until you get to the very end, and you want to round at that very end. So that's really important, as you're doing these sort of calculations. Any questions on that there? So obviously there's some equalities that you're familiar with, and we see again 1 inch is 2.54 centimeters, 12 inches in a foot, 5,280 feet in a mile, and those type of things. Again, for any of these we could write conversion factors for that we could use in dimensional analysis. Remember that we do use prefixes, right, for the metric system, things like mega, right, which is big M, and 10 to the 6th, or kilo, which is K, 10 to the 3, deci, which is D, 10 to the minus 1. We've used nano, I think, the other day. Nano is 10 to the minus 9. Milli, which is a common one, right, which is M, 10 to the minus 3. Remember that when we use these sort of prefixes, again, for example, like kilo, and this again is something that people commonly mess up on when they go to a chart like this and they're looking at those things. Remember that what we see there is how much there is in the base unit to one of the prefix units. So what I'm talking about again is if we're looking at grams to kilograms, for example, the base unit is grams. The prefix unit here is kilograms. So if we were going to find a relationship to use, what that 10 to the 3 would tell us is there is 10 to the 3 grams in 1 kilogram, right? Basically 1,000 grams in a kilogram is basically what that means. You know, if I was using nano, that would mean that there are 10 to the minus 9 grams in 1 nanogram, right? It doesn't really matter what unit you're using. Grams could be centimeters or meters, and that's the same idea as there's 10 to the minus 9 meters in 1 nanometer. Here, the base unit is meters versus grams. So it doesn't really matter. The prefix works the same. So it is super common that people always do it backwards, like in 1 gram, there's 10 to the 3 kilograms. And again, very common mistake when people look at those equalities, they kind of shoot them backwards. Any questions on how to use that conversion? Couple other things, obviously volume, a couple conversions and things that sort of mean the same thing that we commonly come across. And that is a milliliter is the same as a cubic centimeter. And that is the same as a cc. This is all units of volume. A milliliter would be like we were talking about earlier. You have some liquid in a glass container, you take a reading and you read off the milliliters or what it is. Cubic centimeters is found by maybe like a square or something like that. You take the length times the width times the height. If you measure each of those in length measurements, which is a centimeter times a centimeter times a centimeter, you basically get a cubic centimeter, which is a volume. These are all length measurements, but 3 of them together gets you a volume. And cc stands for cubic centimeter. So that's what basically it means, same idea. cc you hear sometimes in medicine, right? Give the guy 5 cc's of this, 6 cc's of this, and they're really milliliters is what they are giving. Any questions on that there? Now, a couple of other important conversions that you hopefully should be familiar with, which is temperature conversions. Temperature conversions. There's 3 different temperature scales that we deal with. That's degrees Fahrenheit, degrees Celsius, and Kelvin. For the most part, it is Kelvin we use the most, and Celsius to Kelvin is one that we use the most. To go from Celsius to Kelvin, temperature in Kelvin is 273 plus the temperature in Celsius. The right number is 273.15. Most people round off the 0.15, and 273 is sufficient. That also means that if you want Celsius, it is the temperature in Kelvin minus 273 would get you there. Fahrenheit and Celsius, temperature in Fahrenheit equals 1.8. The temperature in Celsius plus a 32. And that means that the temperature in Celsius would equal temperature in Fahrenheit minus minus 32. Divided by 1.8. Also important is for Fahrenheit, we do degrees Fahrenheit, degrees Celsius, no degrees here. It's just Kelvin and stuff like that. Now, again, pretty much this is the one we'll use the most in chemistry. This one probably the second, and probably not very much of this at all along the way, but it is a good one because if you are given a temperature in Fahrenheit, you would need to convert it to Celsius, so you can then convert it to Kelvin, and vice versa. If you had Kelvin 1 and Fahrenheit, you would have to kind of go through these kind of conversions on the right. Where does the 1.8 come from? It really comes from the difference between the freezing point and the boiling point of water on each of these temperature scales. Boiling point of water on the degrees Celsius is 100 degrees Celsius and 0 for freezing. And the difference between sort of freezing and boiling is 100 units on one And then for Fahrenheit and so forth, it's about 180 units difference. And that's sort of where the 1.8 comes from. 1.8 is also like the fraction you might have learned, like 9 over 5 is the same thing as 1.8. And because there is sort of a variety of sort of numbers you could use to do these conversions, when we're talking about temperature conversions, including that most people just use 273 instead of 273.15, there is sort of a special thing that we do when we're talking about conversions of temperature and temperature alone. And when we're doing a straight temperature to temperature conversion, we make the answer look like the original number. So the converted temperature should look like the original number. So what does that mean? It means, well, if we have, say, 32.5 degrees Celsius and I want degrees Fahrenheit. If I did that, I would put this, and hopefully this number will work out all right. I would put that into this equation here. Temperature in Fahrenheit would equal 1.8, 32.5 plus a 32. And that would give me 1.8 times 32.5 plus a 32. And that gives me 90.5 degrees Fahrenheit. And the original number went to 1 decimal place. Our converted number would also go to 1 decimal place, and we would do that as well. Now, let's say we had 40 degrees Celsius and we wanted Fahrenheit. We put that number in, we end up with 1.8 times 40 plus a 32. And if we do that, I'm sorry, let's do 44. Let's do 44 so I get a better number here. 44. There we go. So we did 44. So 1.8 times 44 plus a 32. There we go. We end up with 111.2 degrees Fahrenheit. Now, my original number here that I keep scribbling out is 44. That is a whole number, which means we would report this as 101 or 111 degrees Fahrenheit, no decimal. So when you're strictly doing a temperature to temperature conversion, and you're not really doing anything else with the number other than taking it from one temperature scale to the other, you should make the converted temperature look like the original temperature. And that what that means is if the original temperature was a whole number, you should take it to a whole number. If the original temperature was to 1 decimal place, you should take the converted guy to 1 decimal place. If it was 2 decimal places, you should take it to 2 decimal places and so forth. So temperature conversions basically follow a slightly different sort of arrangement than what we do with normal sig figs. And again, basically original number is what the final number should look like in terms of decimal places and all those kind of things. And obviously if we had temperature in Kelvin would be 273 plus 44 if we were doing that. And that would get us, again, 273 plus a 44, 317. Again, Kelvin, no degrees written there if we were doing those conversions. Any questions on temperature conversions? Obviously, you do need to know how to do these. And like I said, this guy box here is pretty much our one that we will use the most along the way. All right, one last thing about conversions here before we kind of move on to the, I think, last maybe topic we're going to talk about here. And that is when we have conversions of multiple units. And what I mean by that is speaking of cubic centimeters, for example. Let's say we had 40, we'll stick with the 44 cubic centimeters. And I wanted to do, we'll do cubic inches, for example, what that would be in cubic inches. Now, it's very common people will really screw up this calculation because they don't really do it correctly. And what I mean by that is, well, these are actually both volumes. They're cubic kind of length measurements. We want a relationship between inches and centimeters. And we know that 1 inch is 2.54 centimeters. So if we were to do dimensional analysis in this conversion, which you should do, 44 cubic centimeters, and you decide, well, the centimeters are up on top, which means when I use this conversion factor here, I obviously could write two conversion factors, which is 1 inch over 2.4 centimeters, or 2.54 centimeters is 1 inch. I would want these centimeters on the bottom. So I would view 2.54 centimeters is 1 inch. Now, if I did this, technically speaking, this centimeter and only one of these centimeters would cancel, which means I would be down to centimeters squared and inches, which means because this is cubic centimeters, I have to do this conversion not once. I need to do it twice, which will take care of the next one, but I need to do it actually 3 times this conversion. First one took care of the first cubic centimeter, second one took care of the second one. Third conversion takes care of all the cubic centimeters at this point. I then would have basically 44 times 1 times 1 times 1. And then I would divide it by 2.54, divided by 2.54, and divided by 2.54. And I will end up with 2.68504474. My units would be inches times inches times inches, which gives me cubic inches. Sig Fig wise, conversion factor, don't have to worry about it. Conversion factor, don't have to worry about it. Conversion factor, really don't have to worry about it. That means, like we talked about before, my original number here has 2 significant figures, which means my answer should actually come to here. With that 8 being there, should round this to 2.7 cubic inches. Now, you could absolutely have done it like this. And set it up there and got this answer. But I will honestly tell you, in my experience, even though people write it like this, they actually forget to actually do it and do this part 3 times. And they end up doing it once and actually get the wrong answer. So again, if you want to be safe, it's sometimes better to write it out step by step so you don't miss doing it. And again, it's super common. Even if people put the 3 up there, they very much forget to actually do it 3 times and they end up with the wrong answer. So if you do it like this on the bottom, make sure you don't forget to actually do the correct math part of it and do it 3 times. Otherwise, again, you will get the wrong answer. Question on that there. Okay. So we talked about Sig Figs, we talked about measurements, we talked about dimensional analysis. Again, this is dimensional analysis up here, how you should properly show your work with your units and everything canceling out. We talked about metric system and SI system and dimensional analysis, how to work out those problems. So I think the last thing that we should need to cover, I think that's in there, is about density. And density is basically the mass of an object divided by the volume. And D equals M over V. Typical units of density are grams per milliliter, are grams per cubic centimeter. And these are the typical units that we see in solids and liquids. As we will see when we get to the gas chapter, for gases, grams per liter is oftentimes the units that we use for density of gases, but probably most of the time these are the 2 units. Again, remembering that a milliliter is equal to a cubic centimeter, so they're a one-to-one relationship. That is a formula, which means you can rearrange it. You could solve for the volume. The volume would be the mass divided by the density. You could also solve for the mass, which would be the volume times the density. Sometimes people remember this by our good friend, the DMV triangle. Everybody loves the DMV. There we go. Density is mass divided by volume. Volume is mass divided by density. Mass is density times volume. So again, that's a way sometimes people will remember sort of density. What's the deal with density? Well, if things are, for example, less dense than water, they will float. If they are more dense than water, they will sink. Right? Now, the mass part of it is pretty self-explanatory. You either weigh out an object, and that's basically how you get the mass. You typically want to convert the units to grams if they're not in grams. There's really sort of 3 ways we could get the volume part in a density sort of calculation. So to get the volume part, the first way is pretty simple. It's sort of what we talked about earlier. You basically fill up some liquid and you actually take a reading, right? So you take a reading and that gives you your milliliters. If it's a solid, we could get the volume by doing our measurements of our length times width times height. As we just talked about, that is how we can get our cubic centimeters. But very, very common in sort of density situations is we get the volume by what is sometimes referred to as volume by displacement. And what that basically means is if we take sort of a glass container and we fill it with some type of liquid, let's say like water, it will have an initial volume. And if we take a solid object and basically drop it in there, what we would expect to see happen is when that little solid kind of goes in there, the volume level will rise to sort of a final volume. And basically the object will displace a volume that's equal to its own volume. So the volume of the object will typically be the final volume of the liquid minus the initial volume. So this is a very sort of common way that we do sort of calculate the density of a particular object is by doing sort of that volume by displacement. Now, you know, so for example, if we had a 52.5 gram sample of a metal and we placed it in 25.0 milliliters of water and it rose to 28.2 milliliters of water. You know, what is the density? Basically, we have D is equal to M over V. We already know that the mass here is 52.5. This is basically the same situation as we just were talking about. We had an initial volume of 25. We put the object in there. It went up to a final volume of 28.2. So the volume of the metal in this particular case would be our final volume minus our initial volume, which would give us 28.2 milliliters minus 25.0 milliliters, which gives us, what is that, 3.2 milliliters as the volume of the object. We then could put that into our density, which would be 52.5 grams divided by 3.2 milliliters. And that would give us 52.5 divided by 3.2 milliliters. That gives us 16.40625. Units here do not cancel, so the grams stay with the number per milliliter. But this is important in terms of significant figures, right? We did several different sort of math parts here. Here we subtracted. So we do want to look at decimal places. And in each case, it went to 1 decimal place, which means we did take the answer correctly here to 1 decimal place. The last thing that we did is actually divide, which means we're looking at significant figures. Top number is 3 sig figs. Bottom number, even though it has 1 decimal place, is 2 significant figures, which means really our answer should end up at 2 significant figures, which would be this right here. So it's really important, again, to make sure that you follow along the significant figures through all your calculations. And again, make sure that you end up with the right number of sig figs at the end. Any questions on that calculation there? Now, one last thing about density, obviously, if we're playing with sort of the density of liquids, and we put different liquids into a test tube that had different densities, we would see this sort of layering occurring, where the bottom layer would be the most dense. Top layer, we'll call that layer up there, would be the least dense. Obviously, if we threw something in there, maybe it just kind of hung out right about there. What that would tell us is that this object that I put in there is less dense than the bottom layer, but more dense than the one above it. And it's somewhere in the middle here in terms of the density of this layer. And that's why it's just kind of hanging out in the middle of those two sort of layers. All right, so that is density. Any questions on density? So I think that pretty much covers all that sort of basic stuff. And again, a reminder that if you want to read more about this, obviously, or review it, it should be, I believe, sort of that pre-chapter in our book, kind of before the first chapter, where all this stuff is covered. You are responsible for obviously knowing all this stuff, and you should be, again, showing your work with units, should be showing your work doing dimensional analysis, showing the units canceling out. You should be giving your answers to the proper number of significant figures, obviously with units involved. When you do, all your work and stuff like that, you do need to know about doing proper conversions and how to do those conversion factors. And obviously, you do need to know how to do density and stuff like that. So we do cover it as we just did here. This is sort of our official, non-official lecture on these topics. And some of these questions may find their way onto the second exam. So just keep that in mind, sort of for the second exam. You do need to know some of this stuff. And obviously, before that, you should still be giving everything, including on the first exam, proper scientific notation. If you use scientific notation, proper sig figs for your answers. You should be, again, making sure that you show your work and stuff like that. Any questions on any of that stuff there?